Okay, decision trees. This is a tree structure classifier, and let me start with giving you a sample training data set. So this is a training data set where it talks about whether a particular person, a student, is able to buy a computer or not. There are multiple dimensions on which this data is being represented. The age of the person, the income in different categories, different income groups. The person can be a student or what do you call? I mean, may not be a student, can be a working professional, whatever. It's student or not. Another feature is the credit rating of the person, and the class label is whether the person is able to buy a computer or not. Right. This is a training data. You are given data with these labels, yes and no's, on, and the data is defined. The labels are yes or no, yes and no's on the field buys computer, and the data is described in terms of age, income, student, and credit rating. And you need to build a classifier, which is a tree structured classifier. It is essentially, if you look at it, it's a classifier which encodes what we call a nested set of rules, and this particular type of classifier is called a decision tree. Decision tree is essentially, can you build a tree structured classifier where at any point given a test, say this is a classifier, a tree or a decision tree which is injected, which is created from your training data, and at any point when a test data is presented in this classifier, it's actually presented to the root node, and based on the conditions mentioned in the root node, you keep taking successive decisions till you reach a leaf node where you will have a pure decision at that point in time. So for example, based on age, you can take a call right at the beginning, and that's what for the response. So given a test point, you will be able to check the age first, and based on the age value, then you say like, okay, if the age is between 31 to 40, this decision tree says yes, yeah, this person is going to buy a computer. So with one feature, you were able to take a decision. And if the age is below 30, you look at, okay, it's a student, yeah, it's a student, then they may buy a computer, and likewise. So essentially this is a tree which is primarily encoding a nested set of rules, and these rules are built around the features on which the data is being defined. And so the training part of this algorithm, primarily what happens in training is you need to inject a decision tree. It's essentially a tree which is collection of decisions based on the attribute values. And in the purest form, every decision is dependent on a single feature. So people have worked on further researched on complicated versions of it. But for the time being, let's assume that every decision, every node is essentially a decision, and every node handles a particular feature, right? And how does these features are selected? We'll come to that. That's part of the tree creation process. So the training part of the decision tree algorithm is essentially the injection of the tree. Primarily, how do you create a tree out of the training data? You're given a training set like this. How do you decide the structure of the tree? How do you decide? How do you index the tree? How do you create the tree? That's called the training part. And the testing part is whenever a new unseen data point is present to this tree, you start going through the decisions in the decision tree, right from the root node till you reach a node where you have the purest form, where the class labels are well defined. All right, I'll give you basic flavor of the decision tree injection mechanism. What happens is what the training algorithm, it's called it's a greedy form of algorithm. In AI, greedy is essentially you take a call as soon as you feel that it's good. That's called a greedy AI algorithm. So the tree is primarily constructed in a top-down recursive divide and conquer manner. Don't worry too much about these jargons out there. Recursive meaning you keep visiting it again and again, any feature or whatever. All right. And divide and conquer, you handle the entire problem, not in entirety, rather you will divide into sub problems and handle it. That's how it happens, and happens in a top down fashion, meaning you keep constructing the tree right from the root node. All right, that's what it is. So at start all training examples, you presume that you have only the root, right? And you need to choose what you call the attributes in the root node with which you'll take the decisions at first, right? Attributes are categorical. So primarily, that's one assumption. Categorical meaning it falls into n categories. For example, the color can be red, green, or blue, right? This is categorical. If it's a continuous valued attribute, what happens is like you can define intervals. If the values you have seen in that particular training data set, age is not categorical, so you say like, okay, less than 30 is one category, one group, 31 to 40, likewise you can do that. So that's, if it is continuous, what you do is you bucket into multiple groups, discretize the particular feature well in advance. All right, and partitioning is recursive, meaning you keep seeing it again and again. Test attributes are selected based on the heuristic. Primarily, like say, we'll come there. How do you decide what to go in a particular node? All right, and when do you stop? When do you stop constructing this kind of a tree, a tree structured form of decisions? When everything is, every training sample is exhausted, meaning you have covered every sample. That's one stopping point. Or else like you have considered every other attribute and you feel that what you call yeah, you have considered everything and you have got enough of purity. So which means that you feel that at the lowest level in the tree you have pure forms of classes. So look at this tree. If you look at the leaves of the tree, this particular tree, you can see like you see no, yes, etc., etc. Right? What it says is when a point goes through all the decisions along a path from the root to the leaf, what happens is like you say that that particular data point got assigned to that leaf, and it may get assigned to a label yes or no. So you have pure forms, but may not be the case always. You can have scenarios, contexts where you may have mixed classes, meaning what do you call it? You have got 30 points falling into this particular group, and 25 belonging to yes and another 5 belonging to no. In that case, majority voting is applied. That's also possible. So it depends on how, to what extent you have constructed the tree and to what depth you have gone into the tree. So that's essentially called the stopping point. Right? You may not go to a level where every leaf is pure. In the leaf is not pure, what happens is like your decisions are primarily based on the majority voting. All right? That's another. So let's look at the tree indection, the basic form of tree indection. The tree indection, if you look at this tree, you must see that the root at the root level, I already told you, every node will, you don't have any tree. Now you are going to start constructing the tree. I have got multiple features to consider. I can take the root level decision with the attribute age, income, student, credit rating, or whatever. Right? I've got 4 options, out of which one should go. It should be selected first. So for this selection, we typically apply a sort of a rating, rather ranking mechanism. And these ranking mechanisms are from well-defined theory in the information sciences, and I'll come there. So we need to choose one attribute where we start building the tree, right? How do you choose the attribute? Based on information theoretic measures. We are going to give you examples of 2. Once you have taken a decision at that point in time, you will get, say you have got the entire training point got divided into 2. Say for example, you have got 3, right? You've got 3 categories or groups in the age. You have got less than 30, 31 to 40, and greater than 40. So based on what you call the first attribute that is chosen, which is chosen based on an information theoretic measure, you get 3 siblings, right? The next or 3 children, and among the siblings, the data, the entire training data will get split into 3. So all those with age less than 30, equal to 30 will fall into one. The training data points will fall there. 31 to 40 will fall into the next bucket, and greater than 40 will fall into the third bucket. Now we'll work on the first leftmost sibling, less than or equal to 30. We'll work with the training points in that bucket, and in that case, what we'll do is, so again, with that part of the training data, we need to take another decision, a lower level decision. We need to choose one of those attributes, and I want to tell you here that age can reappear, right? But age reappearing again at this level doesn't make any sense. And because so reuse of an attribute is a possibility, but in this trivial example doesn't make any sense, because see, I have only age less than or equal to 30, so it doesn't make any sense. But if you want to go further, there are attempts on reusing an attribute, and decision tree allows that. So what you do is you work only with the training points with age less than or equal to 30 on the leftmost branch, with 31 to 40 in the branch in between, and above 40 on the rightmost branch. And with those training data, you need to choose another attribute based on the information theoretic measure. Then you take decide which is that attribute, and then you choose that attribute, take a decision on that attribute, and you keep building the tree. This is how the trivial decision tree building algorithm works, right? And since we are like taking, say for example, at the highest level of this hierarchy of those tree, anybody who is less than or equal to 30 is partitioned into one group. Between 30 and 40 is another group, and greater than 40 is another group. So these kind of trees where what do you call, your decisions are based on, say for example, if you're plotting and the attribute age along an axis, you can see that what do you call, age less than or equal to 30 is equivalent to drawing an axis, drawing a line parallel to the axis age, right? The age axis, essentially like in that axis at 30 you do a cut, you do another cut on 40, you do another cut on greater than 40, whatever, right? You get 2 cuts which will essentially divide the entire region into 3 parts, in the entire range of ages into 3 disjoint groups. And these kind of partitioning is typically called axis parallel partitioning. And these kind of trees, which essentially uses single attributes with axis parallel cut across the values, are called axis parallel decision trees. So what we are going to see is axis parallel decision trees, and I'll ask you to, maybe towards the what do you call, end of the session, the course, I'll ask you to, some of the groups, to work on a new form of decision tree, which is called oblique decision trees. We'll come there later. So all I want to say is, like, the categorical split, disjoint split of or on any attribute with one attribute considered at any node, such decision trees are typically called axis parallel decision trees, because the primarily the decisions are essentially axis parallel splits across the attribute being considered, right? So how do you, so let me do a recap. At any point, we start with the entire training data. That's our starting point. We need to choose an attribute over which the split has to happen. How do we choose it? You use an information theoretic measure. Let's go back and look at that information theoretic measure, where you can choose the attribute to be considered at any point in time, right? So the first information theoretic measure I want to consider is called information gain. Information gain, it comes from the information sciences. This is how it's being computed. So you've got a data set D, which is primarily, like, you can presume that that's your training data. D is your training data, and you've got multiple classes. You've got CIs, these are the classes. You've got two classes here, yes or no classes in our particular case. And you can see that the information content of, or it's also called entropy. Entropy is basically like it must be a term very familiar to the people coming from a physics background. Entropy is defined as pi log pi, logarithm to the base 2, summed over all the points. Right. So what is pi? Pi here is the probability that an arbitrary tuple in D belongs to the class I. So in our case, we have got two classes. Let's look at the data. Right. You have got two classes. What are those classes? Bias computer yes and bias computer no. How many are there in this training data with bias computer yes? If you look at it, I see that there are one. I can count it: 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 records or tuples in this data with the class yes, and there are totally, I think there are 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So there are 14 training points, out of which 9 says yes as the class, and which says that another 5 should say there are the class is no. So that's our current context. So from to compute the information theoretic measure, PI would be no split. PI is like, it's a probability that an arbitrary tuple belonging to class C1. So the probability of an arbitrary tuple belonging to class S would be 9 by 14, and the probability that an arbitrary tuple will belong to class no would be 5 by 14. I think that's clear to you, right? So 9 by 14 and 5 by 14, that becomes our PI values. I is equal to, so we have got, how many are there? We have got, yeah, PI is basically the I is essentially the number of classes. So we've got two classes, information, expect information or entropy, computed over their entire training point. When there are two classes in our context would be computed like this. So information, the entropy of D would be minus 9 by 14 log 9 by 14 minus 5 by 14 log 5 by 14. It will be, it roughly comes to 0.940. I think must be clear till now. If there are any concerns, you can stop here. All right, that's basically the entropy of the entire training data. All right, and the information after, so now we can do is like what we do in decision tree, we can split the data over multiple attributes. I've got 4 choices. I've got age. I can split the data either at the root level. I can split either on age, either on income, or on student, or on credit rating. Right? We can split it on either of these attributes. So which one to choose, right? So I've got 4 choices. So I need a mechanism to decide what to be my choice. For that, what we do is we can compute, we can take every attribute as a candidate. Let's take age as a candidate. When age is taken as a candidate, age will split data along the axis age. We have seen that data will get partitioned to less than or equal to 30 age. 31 to 40 is another group, and we'll get what you call the other group greater than or equal to 40. All right, that's the next group. So the information, the expected information after the split over age would be, how do you compute it? The cardinality of the split, all right, divided by the cardinality of the data set into information, expected information of the split. That's how it is. Let's look at an example. So this is our age. Along the age, I've got 3 groups, and if you look at it on the table which is shown on the left side, you can see that so in the age less than or equal to 30 group, right? So this record goes in, this record goes in. then there is this 3, 4, 5. Yeah, there are 5 what do you call tuples, or 5 records with age less than or equal to 30, right? 5 tuples, out of which you can see that these 2 tuples have label as no, right? But this also has label as no, and this has label as yes, and again one more is with label as yes here, right? So these 2 are labeled with yes. So age less than 40 group among the training data. So there are 5 tuples, 5 records, out of which 2 have, so that's where pi and ni. Pi, it denotes the probability of yes, and ni you can presume that it's a probable, it's not the probability count of the records with yes, and ni is the count of records with no. Out of the age less than 30 group, 2 having yes and 3 having no, right? So how do you go about do this? And likewise, you can count 31 to 40. All are positive, no negatives, no negative class members, and above 40, you can see 3 are having positive and 2 are having negative class. And how do you compute information of along age? We are considering only the age. Age will split data into 3 categories, right? So the first category, less than or equal to not 3 category, 3 groups. The less than or equal to 30 group has 5 members, 2 positive and 3 negative. So 5 members out of 40. So cardinality of the first group less than or equal to 30 is 5. The total cardinality of the data set, training data set, is 14. So 5 by 14 into I23. What is the information content of 2-3? Basically like 2-3 split. How do you get it? You get it from here. So 2-3. So what will be pi in that particular group? Pi will be 2 by 5 for this particular positive class, 2 by 5, and the what do you call, for the negative class in this particular group. The next one would be for the other class will be 3 by 5. All right, 2 by 5 into 3 by 5. So in the equation, the computation would be like this. So out of so we are considering the 5 by 14 to I23 is essentially corresponding to the group less than or equal to 30, 5 by 14. So if you look at that equation, what is here? It's cardinality of the group divided by cardinality of the entire training data into the information, what do you call, expected information, the entropy of that particular group. So which is computed from here. So 5 less than or equal to 30, 5 members over here, 5 by the entire training cardinal data set cardinality is 5 by 14 into the value of that particular group computed with this equation. You got what do you call, pi. There are only 5 elements there, out of which 2 are, you can see that 2 are belonging to the positive thing and yes class, and 3 are belonging to the no class. So 2 by 5, and then the other one would be 3 by 5. So you compute the result would be 5 for this is for the group less than or equal to 30 by 5 by 14 into minus of what do you got, minus of 2 by 5 log 2 by 5 minus 3 by 5 log 3 by 5. That'll be the I23 computation. And likewise, you can look for the other next class 31 to 40 group, this next category. So there are 4 elements here. So your next term will correspond to that, 4 out of 14. 4 is the group size, cardinality of the group divided by the entire training data, I40. So I40 will have pi will be 4 by 4. It's 1 log 1 plus log 0. So it's essentially 4 into log 4. It's essentially like pi would be 4 by 4 and the other would be 0 by 4. So what happens is like 4 into pi, it's basically like 4 by 4. 4 by 4 into 1 log 1 plus 0 into, so that term will go up, so minus So which says that you get minus 4 by 14 into log 1. So essentially like that's how you compute. You essentially you have to consider the next group also. Next group is you see that it's greater than 40 group, and likewise you can compute it for so 3 by 5 and 2 by 5 would be the pi values out there, and 5 by 14 would be the because there are 5 elements in this group. So what you do is you compute this particular the expected information after split over each. So you get some value, all right? You get some value. So information gain is essentially defined as the information gained by branching on attribute A. Information gain by attribute A would be right information, the entropy. So the entropy of the data, the training data minus the entropy, primarily like the entropy after the split. The primarily like what do you call how the split would affect the entropy. So that's what it is. That's what is being computed over here. Information expect information over the entire training data minus expect information after the split. So why do you say that it's a gain? Primarily because once you split, you get a more pure form of data being represented after the split. So that's where it's called, and that's a semantic behind calling it information gain. And information gain is computed by you compute the entropy of the entire training data, and then you find the expect information or the entropy after the split over a particular attribute. So you find the difference, and that's called the information gain. So you can do it by you can do it for, this is computed for age. Likewise, you can do it for income. You can do it for whatever the credit rating. These are the 3 other things. So information gain. So you got for the training data, the entropy was 0.940, and for this is what it is, and you get the difference. This is what you gain, right, by splitting over age. So this is what you gain by splitting. If you have similarly, you could have computed for income, you could have computed for student, and you can compute for credit scoring. And so which one you will choose? You will choose that particular attribute where the gain is maximum, information gain is maximum. So that's what it is. That's what it is. So this is one of the information theoretic measures with which is conventionally popular, I would say, in the decision tree indexing algorithms. So this using this particular mechanism, what you do is when you index a tree, when you want to index a tree, what you do is you consider all the, you can compute the, for your training data, you compute the entropy, you compute what you call the expected information after the split over each of the attributes. Then the attribute with the maximal gain would be considered for the split. You keep doing it recursively for every other what you call split, and you keep constructing this tree till you see that you have considered all the attributes. That's one way. Or else you have seen that all the what you call resulting leaf level nodes are at a purity that you intend to have. So either everybody in the leaf is belonging to the same class, and you stop. You can also stop at points where you see that I had enough of depth. So this is another considered. So you say, okay, I'll index the tree only to a depth of 5. People are considering such convergence criteria also, primarily like criteria, stopping criteria also, not convergence, but stopping criteria also. So that's one information theoretic ranking of attributes for building the decision tree is one. There's another interesting ranking mechanism is called Gini index. The Gini index is essentially if a data set contains examples of n classes, the Gini index is defined as 1 minus pi, where pi is the relative frequency of class J and D. So in our case, you can see that what you call, you've got 9 tuples yes and 5 no. In our 14, the original training data, I've got 14 training points, out of which 5 are 9 are yes and 5 are no. So the Gini index of the entire training data would be say 1 minus 9 by 14 the whole square minus of 5 by 14 the whole square. So this is what it is, the Gini index. You compute the Gini, and so essentially you use the relative frequency or probability of deciding whether a randomly chosen point is yes or no class. That's what it is. The probability is essentially taken out there, and you compute the Gini index, and then very similar to the mechanism that we have seen on each of the other partitions. What you do is you compute, if a data set D is split on A, you compute the Gini index after the split on each of the attributes. If a data set D is split on attribute A in two subsets D1 and D2, in our case A can be the age, then you compute Gini of the data split over. So what you do is you have, again, it's again, the weighing mechanism is similar to the information gain context. So D1 is the split, and D is basically you take the cardinality of D1 by D into Gini of D1 plus cardinality of D2 by D into Gini of D2. So essentially, like, I mean, it's a measure of impurity. So the reduction in impurity would be Gini of A will be Gini of D minus Gini over the Gini computed, index computed over the what do you call it, over the split. The attributes providing the smallest GD or the largest reduction in impurity is chosen as a split in the node. So that's essentially the point. So again, you have, you treat these as, these are not the this is not an exhaustive list of the ranking mechanism, primarily the attribute ranking mechanism for creating a decision tree. You need to, again, in this particular example also, you must have a particular computation also, you must have realized that you need to consider all the candidate attributes at any point in time and compute the corresponding ranking, and then based on the ranking you choose the attributes with what you call, which has the maximum benefit when it comes to the split, and then you keep building it. All right, you can see that computation, you can have a look at it and you can compute it offline. So that's how the tree is actually built. So you start with the entire training data, then you essentially need to, you presume that the entire training data is at the root. So out of the available features, you need to do a split on one of those features. You rank the features based on an information theoretic measure such as information gain or a Gini index, or there are similar mechanisms also there, or other mechanisms also there. People are still researching on it. So based on that ranking, you choose one attribute, do a split at that attribute. So your training data get divided into multiple pieces, right? You get child nodes, and for each of the child nodes, you repeat the same process, right? You keep doing it till you see that you have exhausted the entire what you call feature set, meaning you have defined a split over all the attributes. That's one way. And the other way is, there are people say like, okay, don't construct the tree beyond a depth of 5. So you do that. That is another stopping criteria. Or you can also stop when you see that all the resulting leaves are pure, meaning, so you are essentially splitting data, the training data, into multiple pieces. And you must have by now realized that these are disjoint groups, right? So each of the disjoint group that falls into a leaf node, if it is in a pure form, you can stop there, right? One of the problem with this kind of a tree construction approach, so this is called the training process, and when a new test point comes in, you do like kind of you present it to the leaf, the root level decision first, and then you keep coming down, right, with that test data. And at some point in time, you realize that this particular test point falls into a particular leaf node, and you report the label of the category of that leaf node as the reported class. One of the problem with this kind of a training and testing approach is one is overfitting. Overfitting is like the model. So the model, you must have by now realized that the model that you construct over a decision tree algorithm is nothing but the tree. The injected tree or the created tree may overfit the training data. It may remember the training data. Too many branches, and right. It may even, like, if they have some anomalies or points which are slightly perturbed, which are outside our correct definition of the class or classes, it may also get remembered by this algorithm, and it may result in pure accuracy. Right, overfitting is one of the problems, and to avoid overfitting, people have come out with different strategies. One of the strategies, pre-pruning. Pre-pruning meaning halt the tree construction early. Do not split a node if it would result in goodness measure falling below threshold. Meaning, if the particular, there is not much of a difference between the split that you get over a particular attribute. You see like, okay, yeah, I don't gain much by splitting over this particular node further, any further, you can stop there. It's called pre-pruning. Post-pruning is essentially like, pre-pruning is a process by which you stop the construction of the tree at any node. You don't go further while constructing the tree. And the post-pruning is like, you construct the tree and cut down the tree, right? Remove branches from a fully grown tree. You have the complete tree built. Then what you do is you can actually, like, as I've already told you, anything beyond level 5 is useless. I can do a cut there. All right. Uses a set of data different from the training data. That's another example. It's basically like you work with a validation data and see whether the validation data is giving you enough of a performance. Otherwise, you say like, okay, if I've stopped my decisions at this point in time, I would have got a better result. So you can stop there, or you can even do hard cuts at a level. So there are multiple, these are post-pruning approaches. So essentially, decision tree induction mechanism is construction of a tree structured model, which is essentially encoding a set of decisions, a sequence of decisions over any path. And you start by presenting the entire training data to the root node, and you keep constructing from there. You will use an information theoretic measure at any point to select a feature that is most appropriate at that level, and then you keep splitting from there, right? Information theoretic measures for feature ranking can be information gain, can be Gini index, and people have come out with new ways of what you call even versions which are taken out from other ranking mechanisms outside the typical information theoretic measures, learned weights and things of that kind. So that's latest research. I don't want to get in there. So all I want to say is decision tree is essentially a model is inducted with a decision tree induction mechanism from the training data. And all you need to make sure while constructing a decision tree is you don't overfit. While constructing the tree, you can pre-prune the tree, or you can, after the construction of the tree, you can post-prune the tree so that the overfitting doesn't happen. And yeah, that's pretty much to start with an introduction on decision trees. What I want you to do is go back, look at open source implementations of decision trees. There are celebrated ones. I can name them right here, but I don't want to do it. I want you to go back, Google search, and I want you to experiment with a sample problem attempted in one of those implementations. There are classic implementations of decision tree algorithms. Just go back, look at it, make a one-page report on decision tree implementation with a simple training tree induction mechanism on a axis parallel decision tree, which is primarily like disjoint across an axis of any of axis which is essentially defined on any of the attributes. So work on axis parallel decision trees. If somebody is interested, go further. You can start looking at oblique decision trees also, which will come back to us maybe at a later point in time. Right, that's all from my side on decision trees for today.